All right, hello everyone, welcome to this video. This is a problem called Walking Through the City from our kinematics lesson, and it is going to be a look at the concept of distance and displacement. So let's begin by analyzing the situation. We are going to have a person who's walking through the blocks of a modern city that's laid out on a grid, and so anytime they're walking, they're either going eastward, southward, westward, or northward. So let's imagine that the person begins walking from the origin point of our XY axes, and we're going to imagine a top-down view of their path. So they're going to begin by traveling forward in the eastward direction, and we're going to describe this motion, this eastward motion, or in our X direction, as being a displacement vector v1. Then they're going to walk northward for a bit, and that's going to be a displacement vector v2. And then they're going to move in the westward direction, and this will be our displacement vector v3. So after this walk, they've moved from this initial point to this final point, and the question is, how much displacement has occurred, and then what is the total distance that's been traveled? And these are going to be two key variables in the study of physics and kinematics. So the overall displacement vector that they're walking through can be described by its own vector, VR, or the resultant vector. And our job is to add v1, v2, and v3 in order to find this VR resultant vector. So let's begin by doing that vector addition using a magnitude and direction notation to define each of these vectors 1 through 3. So this is going to be a magnitude, direction notation. We're going to use like an ordered pair of numbers and write one for each vector. So we start with the first vector, which is v1, and it has a magnitude of, let's say, 0.3 miles. And just so you know, I'm grabbing these numbers from our problem statement, but you could do this problem with whatever numbers you wanted to. This is going to have a direction. Direction is like an angle, and we're going to make, as a convention, all of our angles measured, positive angles measured counterclockwise from this positive x-axis over here. So angles going like this. So this is going to be, because it's purely in that positive x direction, 0 degrees. Then we can have vector 2. This is going straight up, so it's 90 degrees positive from that axis, and it's going to have a magnitude of, let's say, 0.1 miles in the 90-degree direction. Next, we're going to have vector 3. This is going to have a magnitude of, let's say, 0.5 miles. And because it's pointing in that negative x direction, this will be an angle, or a direction, of 180 degrees. Okay, so we've defined our vectors. The next step to adding them is actually not to add these numbers together. We can't just add these magnitudes because vectors aren't regular numbers, or they're not scalars, quantities. They are vectors, and so we have to add them by components. So let's create a new section here to create our x and y components. X and y component notation for our vectors. So we go back to v1, and we can see that it has a purely x component and no y component. So we will write it as 0.3 miles, comma, 0 miles. We move on to vector 2. Vector 2 is pure y and no x, so it's going to have 0 miles for x, and it's going to have 0.1 miles for y. And now the tricky one is v3. It has purely negative x, so it's going to be negative 0.5 miles, and its y component is going to be 0 miles. So we've changed here from magnitude direction notation to an x and y component notation. Okay, so our next job is to add these three vectors. So let's go here and create a section for our resultant vector. And we are going to find that in component notation. And so all we need to do is say that VR is equal to the sum of all the x components from before. We can first actually write it as a vector equation, saying that we're explicitly adding these three vectors together, but that sum is going to be written down by adding up these x components and these y components. So for example, we'll have here for the x component of VR, which, by the way, if we look at our diagram, is going to be this guy here, VRX. This is the x component of VR, and this is going to be the y component of VR. This x component will just be 0.3 miles plus 0, I'm adding these three numbers, plus negative 0.5 miles, comma, and now we just add these three. So 0 plus 0.1 miles plus 0. Okay, the negative 0.5 and the 0.3 come together to give us negative 0.2 miles. And over here for y, we just have positive 0.1 miles. Okay, so we now have the x and y components. This negative 0.2 is like the VRX, and the 0.1 is the VRY. So now that we have those, we can actually go in and find the magnitude of VR, which is basically the length, is represented by the length of this vector in the diagram. And so we're going to say resultant vector magnitude. Okay, and so for this, we're actually going to invoke what's called Pythagoras' theorem. If we come back to our diagram, we see we have essentially a right triangle here. And if we just think of these sides as a, b, and c, we can have a squared plus b squared equals c squared. So writing that in the notation of this vector, we're going to have the magnitude of VR is equal to, or the magnitude of VR squared is equal to Vx squared plus Vry squared. And we can just take the square root of both sides and then have the magnitude of VR is going to be the square root of these two quantities. So here's the 0.2 miles squared plus 0.1 miles squared. And you can notice that I dropped a negative sign here, but that's okay because it's getting squared anyways. So it'll be the same value. So this comes out to be approximately 0.22 miles. And that will be the magnitude of our resultant displacement vector, which is the magnitude of this, this displacement. Takes us from the start point to the end point in a straight line. So that's our displacement from our starting point. Okay, 0.22 miles. So now we'd like to find the direction of that vector. Essentially, we want to find this angle right here, theta r, to report with our magnitude, because remember, all vectors have a magnitude and they have a direction. So to do that, I'm going to switch to another page because we're out of room. And let's draw another diagram, just this time of that VR vector, that resultant vector. And so here it is. So we said before that it has an x component, VRX, and it has a y component, here VRY. We're trying to find this angle here. This is theta r. And we could also define this interior angle theta, and of course this is 90 degrees. So we now remember our right triangle trigonometry, forgetting about the fact that these are actually vectors. These are essentially line segments making up the sides of a triangle. So we can go to the definition of the tangent function for this right triangle. The tangent of that interior angle theta is actually going to be equal to VRY over VRX. If you think back to your SOHCAHTOA mnemonic, this is saying we're doing the opposite side over the adjacent side of this triangle. So with that expression, we can now do the inverse tangent of both sides. On the left-hand side, the inverse tangent and the tangent will cancel out, leaving just the angle. On the right-hand side, we will have the inverse tangent of VRY over VRX. We can now plug in the numbers. VRY is going to be 0.1 miles, and VRX is going to be 0.2 miles. And so that angle will come out to be 27 degrees. But that's not our final answer, because remember, we're using this convention of giving all direction angles from the positive x-axis. So if we have this angle here is 27 and we want this one, we remember that the whole half of this xy plane is 180 degrees. So if we do 180 minus this 27, we'll get the theta r, which is the one that we want. So let's just write that here. Theta r is equal to 180 minus theta. So theta r is equal to 180 minus 27, and these are all in degrees. So theta r is equal to 153 degrees, and that will be the direction of our displacement vector here. Okay, the last thing to do is to compute the distance. Oh, and let's just add a label up here. This was the resultant vector direction. Okay, so now last section we're going to have is going to be the distance, like the total distance that's been traveled by the walker. And so to get the distance, we're actually going to end up adding the magnitudes of all the displacement vectors. So distance will just be equal to 0.3 miles, that was the v1 magnitude, plus 0.1 miles, plus 0.5 miles. Here we're completely ignoring their directions, we're just adding their magnitudes. That total will be 0.9 miles. So the moral of the story, if we just go back now to the first page and take a look at this, we can see that walking down the streets, going on this grid, we went eastward, northward, westward. If you add up those three distances like we did here, you'll get a bigger number, almost a mile. Whereas if you go in a straight line path, as the crow flies, it will go from this origin point to the final point along a straight line path, and obviously that will be a shorter path. So your distance and your displacement will only be the same if you're traveling in a straight line from start to finish. If you take another path, as was taken here, the distance will be greater than the displacement. Another difference is that this distance quantity is just a scalar number. It's just a regular real number, whereas the displacement vector has a magnitude and a direction. So it has a certain magnitude here, and then it also has a direction of where that magnitude was taken in. So there you have it, guys. Walking through the city problem, core concepts of kinematics are displacement and distance, and we've covered them here. I hope you've enjoyed this, guys, and I'll see you in the next video. Thanks very much.